Hello, my name is Joshua Martinez, and I'm going to be going over the general line coordinates in 3D. So the developer of these ideas is Dr. Boris Kowalczuk, and then the ideas were implemented inside of the 3D engine Unity by myself. And then the presentation was made by me and then edited by Dr. Boris Kowalczuk. We're from the Department of Computer Science and Central Washington University in the United States. So that being said, here's what I'm going to go over here in this presentation. First, I'm going to introduce kind of what we're going for with our program, general line coordinates in 3D. Then I'm going to be going over some prior work, things that are fundamental in our own program. And then I'm going to be going over our own program specifically. And then a quick kind of demonstration of how our program might be used by user. And then finally is just some afternotes. So that being said, general line coordinates in 3D. So I'm just going to read this first goal here and then explain it. So we want to allow a user to intuitively understand visual aspects and patterns of data. So in other words, what we really want is to allow a user to be able to kind of fiddle around with data that they choose and to understand it, understand what's going on, what certain attributes have an effect on, and things like that. And so I just want you to kind of keep this goal in mind as I go throughout this presentation. But before getting into our work, let's go over some fundamental to our project prior work. So first we have the general line coordinates of linear, written by Dr. Kowalczuk, and it's in the Visual Knowledge Discovery and Machine Learning textbook. And then we also have shifted paired coordinates in the self-service data classification using interactive visualization and interpretable machine learning paper. So first let's go over the general line coordinates, linear or GLCL lines. So the goal here is to display the effect of a data attribute, it's important that it's a data attribute, on its total linear function. So let's consider that we have two normalized points, meaning that their values are somewhere between 0 and 1. We have the first point x, which is a data point, meaning it's retrieved from some file, whether it be a row from the iris dataset or a row from the Wisconsin breast cancer or the mushroom dataset. And then the next point we have is an a point, it's called a, which has two attributes just like x, and it's a user inputted point. This means that the user inputs it one time and it affects the rest of the data inside of a linear function. So that linear function here is basically all the attributes of x1 multiplied by the attributes of their corresponding attributes of a added together. We form a linear function in that format, as you can see. So in our case, it's a1 times x1 plus a2 times x2, since we have two attributes, right? And now for the sake of just kind of simplicity and just getting some numbers on the screen, let's assume that a1 times x1 equals 0.4, and let's again assume that a2 times x2 equals 0.2. And then when we add those together, we get 0.6. Now you'll notice that there's some highlighted numbers here. If you look at those corresponding colors in the picture on the right, you can see what those numbers visually represent in the GLCL lines. So the f of x function total, its height is represented along the z-axis, and again it's the total height of the GLCL line. Now the GLCL line is in white. It's basically when we visualize this, we only show the white part. The yellow, the blue, and the pink are all just to explain what's going on here in this particular picture. So the pink represents the height on the z-axis. And then, of course, the subcomponents of that are the blues, so each segment has a height, right? Each segment tip has a height, which is one of the values from one of the clauses from the function. And then the segment itself is made of two segments, x1, and the length of the x1 segment is the same value of the attribute x1 from the point x, right above the top left of the slide. And then x2's length is the same value of the attribute x2 from x. Now in order to have these values fit such that their combined height reaches 0.6, they have to be bent a little bit. That is, unless the attributes of A all equal 1. If the attributes of A are anything less than 1, then the line itself is not bent because the height is just the added attribute size, right? But anyways, to get these angled lines, what we can do is take the arc cosine of A1, just because of how these heights are, gathered, and take the arc cosine of A2 for the second segment, and these angles allow us to have these height added points with the x1 and the x2 length segments add up such that their heights reach f of x equals 0.6, and this is a GLCL line. Again, its purpose is to find the effect of a data attribute on its total linear function. So if we look at this white line, we can see that x1 has a much greater effect in both the height and the length on the total linear function. So in this case, x1 is the data attribute with the greater effect. Now let's move on to shifted paired coordinates, or SPC. So the goal here is to visually represent high-dimensional data without loss of information. Now, when we consider, say, a 2D point or a 3D point, those things are pretty easy to kind of visualize, right? We see it all the time in just everyday life. But when we consider something like, say, a 20-dimensional point, it's a little bit harder to visualize. In fact, us being humans can't really do it, so easily. But that's where the shifted paired coordinates comes in. It's a way to visualize a point in any dimension. So let's look at the point U. It's in green. It's a 6-dimensional point, and we want to represent this point visually. So the shifted paired coordinates, what it has us do is it has us take 2 attributes from this point, every 2 attributes, and it puts it into its own 2D subcoordinate. And then it connects these attributes into a line which shows the point. So if we look at the U green, the green line in the subcoordinates, we can see there's U1, U2, U3, U4, and U5, U6, which are all connected in a vector which represent the point U. And then you'll notice that there's some rectangles. 3 to be specific, 1 in each subcoordinate. These rectangles together represent one rule. So all of these rectangles are one rule. Now when we look at the point U, we can see that U1, U2 is inside the first rectangle, R1. U3, U4 is inside of the second rectangle, R2. And U5 and U6 is inside of the third rectangle, R3. This means that the point U fits within the rule made by the 3 rectangles. Now if we look at the point K, another 6-dimensional point, we can see that K1, K2 is inside the first rectangle, K3, K4 is inside the second rectangle, but K5 and K6 are outside of the third rectangle, meaning that K is not part of the rule made by these 3 rectangles. So now let's go into our work. The picture on the right is the IRIS dataset represented in SPC, or shifted paired coordinates in 3D, which is SPC 3D. This is specifically the IRIS dataset, and I'm just gonna, for the sake of simplicity, just note that the Setosa is the red class, Versicolor is the green class, and Virginica is the blue class. But I'll generally be calling it the red, the green, and the blue class. So let's explain the shifted paired coordinate 3D method. On the top, we can see what the shifted paired coordinates for the IRIS dataset looks like in 2D. Now if you look at the left subcoordinate, you'll notice that the red and the green and the blue are all kind of a little bit mingled up, and it's sort of hard to differentiate them. Whereas if you look at the bottom picture, again in the left subcoordinate, they're fairly separated. So this is obviously the key difference of SPC 3D, is that there's height. This height is, for a purpose, the same function used in the GLCL lines. Now, when we play, this picture here is even more separated than the last picture, and it's because we played with the modified A vector, the user inputted, if you remember that. And so our goal here when we did this was to isolate all the classes. Now we've done a pretty good job here. The red is fully isolated and the green and the blue are fairly well isolated. If we look at the yellow line, which is called the discrimination line, it's used to kind of give a relative 3D effect. But we can see here it's at the point where the green and the blue class meet. And so what we want to do here is we want to try our best to isolate the green class. And we could have done the blue class as well, but we just chose to do the green class. So we've made two rectangles that you can see in white, made by the user, which do a pretty good job at isolating the green class. But if you look closely, you still see some blue, right where the discrimination line is, just slightly above the blue class. And so if we go one step further, this is a top-down view of the right subcoordinate. So the white square is our old rule, which we had, and the yellow square is a new rule which we want to make, which would effectively eliminate the rest of the blue class, the blue lines from the blue class. And while it does also eliminate some green points, the fact is that there's still quite a few green points within the rectangle, so it's still pretty good. And as we can see, once we do that, the green class is fully isolated. Now let's go on to GLC in 3D. So basically, key difference here is that the base of the point does not start at 0, 0, whereas it does in 2D, but instead it starts at its corresponding point, which the attributes come from. So that's the difference with that, and it's useful because while the SPC gives us a concentration of points, which is helpful, just for seeing data where it's located and value, the GLC allows us again to see the attribute effect. So using this concentration of points plus the attribute effect allows us to kind of quickly make some rules, which I'm going to show here, or at least explain how a user might start to make rules. I'm not actually going to make rules for this myself, but let's reiterate what the rules are here. So our goal is to allow a user to intuitively understand visual aspects of patterns in data. Or in other words, we want to allow a user to play with data to kind of understand what's going on. So let me get inside of what I imagine a user might do in this case. So let's say our goal here is to isolate the blue class. What a user might do is they would look at where the blue class is located inside of the shifted pair coordinates, so where it is on the base plane. And they might notice that the blue class is mostly made of high values because it's in the corner of either cube, right? So all of its attributes tend to be higher values. And then on top of that, what the user might notice is that of the blue class, the third segment seems to have the consistently greatest effect on the class as a whole. So what the user might do in this case is they might try to make a rule which specifically targets the third attribute and high values of the blue class in order to try and isolate it. And so again, I'm not going to make a rule, but I'm just trying to show what a user might try and do as they're making rules for themselves. So now on to future work. So as you saw, we had rules for each subcoordinate, but once we get into larger data sets, like the mushroom data set here, it kind of becomes a little bit difficult to make rules for each subcoordinate in terms of UI and in terms of just making it easy for the user. So one way to potentially help this is with VR, allowing the user to modify the rules with their hands, and then that rule is generated into numbers automatically. Also having rotatable rectangular prisms instead of the rigid, flat, 90-degree angle rectangles, which could create more dynamic rules, although it also might be too complicated, so we'll just have to implement it and think about it and see. And then some more feature work from SPC 2D. As you can see, they have a very useful aspect which cleans up their visualization. So when they have a whole bunch of messy points, they combine their points right into the classes nearby. They combine nearby points basically into their classes, is what I'm trying to say. And that's something our program doesn't do, but could be very helpful. Another thing that the SPC 2D does is it allows multiple rules per subcoordinate, whereas ours only allows one rule per subcoordinate. And then they also allow the shifting of subcoordinate axes. So whereas our program might go x1, x2 in one subcoordinate, x3, x4 in another subcoordinate, we would otherwise be allowed to do, say, x1, x4 in one subcoordinate, and then x2, x3 in the other subcoordinate. This is just useful for, again, playing with the data and trying to understand it as best as we can for the user. And with that being said, here are the references, and thank you for listening.